Okay, so the first thing I'm going to do is I'm going to open this affairs data, and it looks like this. I see many of you are there. You're not going to be able to edit this though. So what you're going to do is you're going to go to File, and then make a copy. And you're going to make a copy, and then you're going to be able to work on it. Okay, so it will look at like something like this, right? This is the data set, and let's go to a pivot table. First, we're going to use this variable male, right? This is the gender variable. I don't know why they call it male, but anyway. And then this categorical variable, it's a binary variable. It has whether you had no affairs or the respondent had an affair, right? Good. So let's select the whole thing. I'm going to do this manually. Oh. And then go to data, pivot table in a new sheet. All right, so you know this. So we're going to ask for the variable affair on the rows, right? Had at least one affair or no affairs. Those are the two values for that one. And for the columns, I'm going to bring this gender variable. And then for the values, add any of the two. I'll just bring affair. Okay. So this is the table, the contingency table, absolute frequencies, right? There's a different number of female respondents and male respondents. So it's better to look at the numbers in terms of percentages to assess if there is a relationship, right? So we go to values and then show the values as percent of column. Now here, we want to assess if there is a difference between in the distribution of affairs between female respondents and male respondents. And when we look at the numbers, well, this is a 2x2 table. It's fairly simple to do that. We see that about 27% of male respondents had at least one affair, and about 23 of female respondents had at least one affair. They're not identical. Actually, male respondents were a little more likely to have an affair, about 4 percentage points. So based on these results, we can say, hey, in this sample, there is a relationship. It's not very strong, right? It's just 4 percentage points, but they're not identical. So there is a relationship in this sample. Now, is that just because of sampling error? Can we say that there is a difference between male and female in the likelihood of having an affair in the population? Because maybe this little difference, maybe it's just there because of sampling error. So we need to rule out that possibility. And that's why we're going to do a test, a hypothesis test, right? To see if this table or this difference, we would also observe it in the population, or if this is just probably just sampling error. All right, so to do that, we're going to do a hypothesis test. And I'm going to start, we're going to need this table, right? We're going to need this table, the absolute frequencies, right? We need the observed, these are the observed values, and we're going to need it for our test. So what I'm going to do is just copy this table and take it to some other, to another sheet where I'm going to do this whole thing. And I'm going to paste the special and put only the values. All right, so this is, and I'm going to call, these are my observed frequencies. These are my observed frequencies. I'm going to paint these guys blue. Okay, this is our table. This is all we need to conduct a chi-square test. Here on the right, you can see I did this before. I have all the steps. I have all the steps here. Okay, so the first step is state the null hypothesis. And the null hypothesis is that there is no relationship between affairs and gender in the population. I'm putting all caps this here because I want you to remember that any null hypothesis has to have the word no, no relationship or no difference between the variables in the population. If you don't say in the population, that's wrong. If you don't say no, that's wrong. Okay, so we're done with this guy. And then the alternative hypothesis, which is the opposite of that one. So there is a relationship between affairs and gender in the population. All right. Again, in the population has to be in there. And there is. Okay, that has to be there as well. All right, good. So now we have to, we're in step 3 already. And that means we need to determine the distribution of the chi-square statistic for tables that come from a population where there's no relationship, right? Well, the null is true. Because we're going to test this guy. All right. So we need to use this formula. Is the number of columns minus 1 times the number of rows minus 1. So degrees of freedom equal to equal the number of columns. How many columns do we have? Don't count the total. How many columns do we have? 1, 2. This is 2 minus 1 times how many rows do we have? Don't count the total. 1, 2. So we have 2 rows. 2 minus 1. Number of columns minus 1 times number of rows minus 1. That's going to give you 1, right? 2 minus 1 is 1 times 2 minus 1 is 1. 1 times 1 is 1. That was fairly simple. Now, this means that for a table of this size, if we were sampling from a population where there's no relationship, these chi-square statistics that we would get from all these sample tables, they would follow a chi-square distribution with 1 degree of freedom. All right, good. Now, determine our critical value for an alpha of 5% and a degree of freedom that we have for this table. In this case, it's 1, right? So for degrees of freedom, 1. And for this, we can use a table, a statistical table. So we would go to the first row where degrees of freedom is 1 and look for that 5%, right, on the tail. But we're going to use the chi-inverse function, which is a lot easier here. So critical value equals. And for this function, you just need two little pieces of information. So chi-inverse, you need to put the probability you want, right? Which it's 0.05 in most social science applications, and then comma. And because, you know, Excel needs to know which chi-square distribution should I look for? And you're going to say, well, you're going to look for 1 degree of freedom. That's because that's the one we're dealing with, right? So Excel needs to know which distribution to look for. That's why we get the degrees of freedom. And if we were looking for doing this in a statistical table, paper or book, then we would also need to know the degrees of freedom. So anyway, chi-inverse for 5% and 1 degree of freedom. That gives us a 3.841. Now, what does that mean, right? This critical value, what does that mean? Remember, this is what it looks, this is what the chi-square distribution looks like when we have these chi-square statistics of tables coming from a distribution where there's no relationship, right? From a population where there's no relationship. And we know that when getting samples from a population where there's no relationship and calculating chi-square statistics for them, we know that we would get chi-square values higher than 3.84, right? Less than 5% of the time, right? If we were sampling from a population where there's no relationship, 95% of all the chi-square values for these tables that are coming from this population where there's no relationship, 95% of those chi-square statistics would be 3.84 or less, right? We would only get chi-square statistics higher than that number if we were sampling from a population where there's no relationship, less than 5% of the time. Okay, now if we change this number, let's say we change it to 1%, that goes up to 6.63. And that means that if we were sampling from a population where there's no relationship, we would get chi-square values higher than 6.63, less than 1% of the time, right? Because we put 1% there. If we put 50% there, that's a chi-square value. We would get chi-square values, if we were sampling from a population where there's no relationship, we would get chi-square values higher than 0.4549, 50% of the time, okay? But we choose 0.05 because we wanna be 95% sure, right? In 95% of the cases, we would get chi-square statistics of this or lower. All right, so that's what the critical value is. Now we know everything about the chi-square statistic when the null is true. Now we turn to our own table. We need to get the chi-square statistic for our table. And for that, we need to do 3 things, right? First, we need to get the observed, which we already have here, our table. And we're going to calculate the table of expected frequencies, right? For each cell. I'm gonna make this a little nicer. Wow, no. I'm sorry, I'm going to edit this. But anyway, so we calculate the table of expected frequencies for each cell, right? And then the formula for getting the expected frequencies is here, right? For each cell, the total in the column times the total in the row divided by the overall total. So I'm just going to copy this table because we're going to need those totals. But we're not going to need what's in there. I'm going to paint this a different color. It's going to be yellow. Okay, so to calculate, and we're going to call this the expected frequencies. Okay, so for each cell, we need the expected frequency here. And that's given by this little formula here, the total in the column, so equal to the total in the column times the total in the row, close parentheses, divided by the overall total, 78. Now for that one, for male that had at least one affair, the total in the column is 286, the total in the row is 150. So here equals to the total in the column, which is 286, times the total in the row, 150, divided by the overall total. And we do the same for this one. For female respondents with no affairs, equal to, the total in the column is 315. Well, same thing. Times the total in the row, which is 451, divided by the overall total, which is 601. It's that one. And for this one, same thing, the total in the column, 286, times the total in the row, 451, divided by the overall total, 601. All right, this is what the table would look like if there was no difference between female and male respondents, right? If there was no difference, this was what it would look like. This would be the expected value. The expected frequencies table tells you what the table would look like if there was no difference in our sample. All right, we have that. Now we need to calculate one more table, and that is the table of chi-square statistics, or the chi-squares for values for each cell. And again, I'm going to just copy these guys. But for this table, we don't really need the grand total, so I'm going to just erase those. All right, and we're going to do different color here. I'm going to make this other pink. To get the chi-square for each cell, we do the observed minus the expected, square that difference, and divide by the expected. So for this cell, equals the observed, but we're going to need some parentheses here. I think 2 will do. So the observed minus the expected, close parentheses, and we're going to square that. And the way to do that is this with this little hat on shift 6, and then that's to the power of 2, right? And divide that, the whole thing, by the expected again. And that's the value of the chi-square for that cell. Now for this one, again, it will be the observed minus the expected, and we're going to square that and divide by the expected. And that is the chi-square for that cell. Now we go with this, the third one, right? Female, no affairs, equal to the observed, 243, minus the expected, 236. We're going to square that, close this, and divide by the expected. And for the last one, male, no affairs, so this is the observed minus the expected. We square that, and we divide by the expected. All right, we have the, we're here. We calculated the chi-square for each cell using that formula. Now we need to calculate the chi-square statistic for the whole table, right? And for that, we add all the cell chi-squares. So here, let's put it just here, chi-square equals, and to get a sum, we'll just use the sum function. So sum sum all of these cells, enter. And we get that our chi-square statistic is 1.56. 1.56. All right. What does that mean? Well, we have to compare our table chi-square with the critical value. The critical value was 3.84, and ours is 1.56. So ours is lower than the critical value, right? Our chi-square stat is lower than the critical value, right? 1.56 is lower than 3.84. What does that mean, though, in terms of our hypothesis test? It means that we cannot reject the null, right? We said that if our table had a chi-square that was very unlikely, then we would reject the null, right? Chi-square statistics higher than 3.84, they would come less than 5% of the time. But chi-square statistics of 1.6 then would be a lot more common, right? We would get them higher than 1.56, we would get them more than 5% of the time. So because our test statistic is lower than the critical value, we make a decision and we say, we cannot reject the null hypothesis. That's our answer. Our chi-square statistic is lower than the critical value, right? That's, I'm sorry, I'm just painting all this so that it's a little more clear. Okay. Now, why is it that we couldn't that we couldn't reject the null? Because our number is we would be pretty likely to get a number of 1.56 from samples that came from a population where there's no relationship. So we can't really reject that hypothesis, but we can actually calculate that probability, right? That's the p-value. That's the p-value. So let's calculate the probability that we would get a number as high as this if we were sampling from a population where there is no relationship. We can use this function, the chi-dist. And for that, we just need to put the number, like the chi-square statistic, 1.56, 048. Let's do the whole thing. Oh. And the degrees of freedom, in this case, 1. If we hit enter, we see that there is almost like a 20% chance that we would get numbers 1.56 or higher. That's pretty common, right? If we were sampling from a population where there was no relationship, we would get numbers of 5.56. Higher than that, 20% of the time. 80% of the time we get lower than that. It's pretty common. So that's why we cannot reject, right? We said we're going to reject only if we get these rare numbers that we only get 5% of the time. But in this case, we can't. So interpret the p-value. That means there is 20% chance that we would get a chi-square statistic of 1.56 if the null was true. That is, if there was no relationship in the population. And 20% is pretty high. So what's the conclusion that we make about the population? Well, we can't reject the null. So we're going to say we have no evidence that gender and affairs are related in the population. That's all we can conclude. If we cannot reject the null, that's all we can conclude. If we would have gotten a higher number here, right, higher than 384, and our p-value would have been less than 5%, then we would have said, hey, there is less than, let's say it was 2%. Hey, there's, 2% chance that we would get a chi-square statistic as high as the one we did if the null was true. 2% is pretty low. So we reject the null that our table came from a population where there's no relationship. And then we can accept the alternative, and we can conclude that gender and affairs are related in the population. So here, we don't know. It seems like there is no difference, right? We don't have any evidence to say that men are more or less likely to cheat than women in the population. We had a little difference in the sample, but we have no evidence to say that there is a difference between men and women in the population, right? And that is how you would conduct a chi-square test.